welcome to the course of Signal and Systems. This is EEE 223 being taught by me. This is my name, Mansoor Khan. Most of the content of this course is going to be taken from Signal Systems second edition, Alan V. Oppenheim and Wilsky with S. Hamid Nawab. Second edition is widely available online. You can go ahead and download a PDF copy of it because most of the discussion that we are going to do and develop for our understanding in signal systems is taken from this course text. Okay. To formally introduce what signal systems are, let's try to develop an analytical framework or a language that an analytical language that we can use to describe what signal systems are. So we begin our development of an analytical framework for describing signal and systems by introducing their mathematical description and representation. So the idea behind signals is, this notion has occurred in many variety of texts. It's some pattern of variations in which the information is contained. Okay, the philosophy behind signal is it's information that is being relayed. Okay, and how this information is being relayed or communicated is through some variations in patterns. So all the signals might have different variable representations, but in all cases, so signals, you see, they can be represented in many ways. But in all cases, the information in a signal is contained in a pattern of variations of some form. So for example, let's consider a certain physical phenomena. Let's consider our simple RC circuit, which you might have come across in your ECA course. So let's say you have a series resistance. Okay, so this is a physical system. You have a voltage source Vs. Okay, having a series resistance Rs, and let's say there is a switch that's turning on and off depending on the charging of a capacitor. So this capacitor is, okay, this is capacitor C over here. Then there's another point where this switch might switch to another point where the capacitor is going to discharge across a certain load RL. Okay, RL is not necessarily the same as series resistor RS. Okay, so let's say we have this configuration. Okay, so what happens is once the switch is in this state, okay, as shown in the figure and in the circuit, the capacitor is going to charge up. Okay, because of the voltage source which is connected in series with the capacitor, which is connected in series with the resistance Rs. Okay, it's going to charge due to this because the capacitor is connected to the voltage source. So now, in the point in time when the switch turns to another position, okay, it comes in contact with the RL, so it is disconnected from the supply. The capacitor discharges. Okay, so for example, if you are interested in the charge buildup, let's say this charge is represented as Q, as a function of time, you are interested in what happens to the charges that are accumulated in the plate of the capacitor. So how the variation of the charge, for example, is varying with respect to time. Okay, so let's say we have the charge as a function of time. You see, once let's say at time t equal to 0, initially the switch is connected to the supply through series resistance Rs, and you will have a charging phenomena like this. Okay, and then let's say when the switch at a certain time instant, okay, and the switch, let's call this time t1, when the switches to the load side, you will have a discharge. Okay, so the charge decreases. And this the amount of decay in the charge is dictated by a time constant which is given as CRL. Okay, you might have known this from your basic circuit analysis course, but the idea is that this trend continues as this switching continues. So with time, you will have another charging cycle, and then you will have a discharging. So this trend, basically this continues as the switching continues. So what what happening is over here is that you have um, you have information that is contained in this pattern that is varying with time. The pattern is that um, in this over the period from 0 to, let's say, t1, you have capacitor that is charging up. So the due to the charging, the charge is built up in the plates of the capacitor, and then once this the switch is switched to the load side, you have the capacitor discharging across the load, and the charge decreases. So this is showing the discharging phenomenon. Okay, so this pattern of variation is conveying an information. Okay, so this the philosophy behind the signal. So this signal is conveying you the information of charging and discharging of the capacitor. Okay, so this is discharging, and this pattern continues. Okay, as the switching action happens. The change in the signal level in this variation showing this shows the charge buildup, charging and discharging of the capacitor. So basically, again, you have a certain pattern of variation, okay, as a function of time, and this shows this basically shows a physical phenomena, which is RC circuit in this case, and it's capturing the information what is going on. Okay, so QT is your signal, okay, and the signal is a function of time as well. Okay, so again, signal is conveying information, so we are getting information from the signal QT as a function of time. Okay, so that's the philosophy behind signal. This what is signal? Signal is an information. Okay, so although it can be represented in many ways, but in all cases, information is contained in a signal, and that is contained in a pattern of variations of some form. As another example, let's consider the human vocal vocal mechanism, which produces speech by creating fluctuations in acoustic pressure. You see, speech is they are sound waves, okay, and they need medium, so they are mechanical waves, which are propagating in the air or in the medium. By successive compression and rarefactions, and these compression rarefactions are supported in the medium and the mechanical medium, and in these variations, in these acoustic pressure variations, is the information that is being conveyed. So again, you see in the pattern of variations, we have information, okay, and this information is signal. Okay, so figure 1 on the next slide is an illustration of the recording of such speech signal obtained by using the microphone to sense variation in the acoustic pressure, which will then convert to an electrical signal. So what happens is that if you speak in a microphone, you produce successive compression and rarefactions in acoustic pressure fluctuations in the air, and these fluctuations are picked up by a diaphragm, which is, for example, vibrating in a magnetic field. It's a coil which is vibrating in a magnetic field, and that in turn produces electrical signals. Okay, so you see in this figure, what happens is that you see there is a certain pattern of variation. Okay, so what is being said is that there is the phrases should we chase. Okay, so you can see these are the in each time frame, in each captured time frame, we have different alphabets. Okay, so different, for example, this particular variation is, as a function of time, is creating this variation, this acoustic pressure fluctuation is giving the information of OUL. All right, should is the part of the should. So SH is a little lower in amplitude. So this variation is the part SH. This part is D. Okay, should. Then you have for V, you have another pattern of fluctuation. For this is W fluctuation. And this particular fluctuation that you see is a little distinct from W. It's E. So this makes V. So then again, on the bottom two time axis, you have another pattern of fluctuation that corresponds to chase, and this A continues over here as well. So you see the same fluctuations, same acoustic fluctuations over here are being continued, right? they end up in SE, chase. So the bottom two graphs are for single word chase. Okay, A is being continued over here, and you see the for each even spoken alphabet, there's a unique pattern in the fluctuation of pressure that is being recorded as an electrical signal by the microphone. So again, these distinct pattern of fluctuations is what we perceive as an intelligible sound, what we understand. Okay, so this different variations are giving us information, distinct information that we are going to the information that we are going to understand from it. Okay, and that information is contained in the pattern, a certain pattern of fluctuations. Okay, so as can be seen in the figure below, different sounds corresponds to different patterns in the variation of acoustic pressure, and the human vocal tract system produces intelligible speech by generating particular sequences of these patterns. So these general particular sequences, they produce intelligible speech, right? I mean, the sequences of these patterns, if we combine them, that's exactly what we are trying to communicate, right? For example, I'm communicating with you and I'm creating certain pressure fluctuations in the air, and then the microphone, for example, of this system is picking up the corresponding electrical signals which are being transmitted to the reception end, and those electrical signals and the variation of those electrical signals is what the information is contained in them. That's the information that is contained in them. Okay, so these general particular sequence of patterns convey information. So signal is information. Okay, so you see, we have seen, for example, we have considered two signals over here. I mean, just to describe the notion or the idea behind the signals, the philosophy. That's the information, and that information has to, because we are saying again that they consist of a pattern of fluctuations. All the signals that we have considered, both the signals that we've considered so far, are are a function of time. Okay, so that means there's an independent variable, that is time. It's a function of time. As a function of time, we have certain pattern of fluctuation, right? So not in all the cases it's the time. For example, what if you are going to measure as a function of altitude? You can have information on for example, the temperature, air pressure, and the wind speed. Okay, for example, these are the information that is required for landing an aircraft, or important for important meteorological data. You have to consider as a function of altitude, height. Down the ground, you need to consider, for example, electrical resistivity or porosity or density of the ground. So those are again the function of height, let's say. Okay, so it's not always the function of time that we have to consider. The independent variable could be any other physical quantity. Okay, it could be time, it could be height. For example, in this case, these are two space coordinates. Okay, so you have, for example, the y-axis over here, and then you have an x-axis over here. This is a picture. Again, it conveys information. For example, if I consider a single point over here, for example, this picture can be broken down into very small identities. Let's call them pixels. Okay, and each pixel is conveying information because each pixel has a different brightness level. For example, okay, for example, this pixel has is the most darkest pixel. This pixel is the light, not the lightest, but again, for the lightest pixel could be over here, the white one. Okay, so again, the signal could be multidimensional. Okay, for example, over here, the signal is it's the function of two space variables. So alternatively, for monochromatic picture, which is shown in figure 2, the signal is the pattern of variation of brightness across the image. So again, the information that is being relayed to you is contained in the variations. There are variations, but those variations are not limited to a single independent dimension of time. It could be multi-dimensional. For example, a picture is again a signal, but it's a function of two independent variables. Okay, so the brightness is a function of two space variables. It could be more than two. For example, in RGB image, it's a function of three variables, right? So signal could be multi-dimensional. Signal could be single dimensional, but most of the signal that we are going to consider for convenience, we are going to limit ourselves to a single dimension. So, and we are going to consider the information or fluctuations over one-dimensional independent variable, and that would be most of the time in all application for in most of the application as far as this post test is concerned, it will be time. Okay. So signals that are represented mathematically as functions are represented mathematically as functions of one or more independent variables. Okay. So you see in this case, for example, if these are acoustic pressure fluctuations, again, this is a function of time. Okay, so these all the graphs are a function of time. And if you want to say that this is acoustic pressure fluctuation, let's call this P of t. Okay, so this pressure is a function of time. Similarly, the charge is a function of time. So signal is the way we are representing the signals over here graphically. Yeah, they are functions. Okay, and their function, the argument that they're going to take inside is the independent variable. In this case, it's the time. So signals are represented mathematically as functions of one or more independent variables. For example, the speed signal can be represented mathematically by acoustic pressure as a function of time, and a picture can be represented by a brightness as a function of two space variables. Okay, so it could be multidimensional, it could be single dimensional. So in this course, we'll focus our attention on signals involving a single independent variable, and for convenience, we will generally refer to the independent variable as time, although it may not in fact represent time in specific applications. For example, if you have to consider, again, if for meteorological data, you have to consider the air pressure, the temperature, density of the air as a function of altitude, height, it's not the time then. Okay, the data has to be plotted against the height, for example. So it's not the time. Okay. Okay. Now signal, there could be there are many classification of this signals. They could be single dimensional, or they could be multi-dimensional. They could be two-dimensional. Similarly, signals, they could be another classification is that they could be continuous time, or they could be discrete time signals. This continuous time, discrete time refers to the independent variable being continuous or discrete. So in case of continuous time signals, the independent variable is continuous, and thus these signals are defined for a continuum value of independent variable. Okay, so for example, in this signal, for example, over here, you can take the amplitude at any particular time. For example, this time could be 1.2 milliseconds. Okay, and then another instant which comes across is, I mean, if the scale is this could be 2 point, for example, 7 milliseconds or 7.2 milliseconds. So the independent variable is taking the value over continuum. Okay, and therefore the amplitude is also taking the value over continuum. So this is a continuous time, a classical example of a continuous time signal. Charging is also the charging phenomena QT. This signal is also a continuous time signal. So on the other hand, a discrete time signal are defined only at the discrete times. Okay, and consequently, for these signals, the independent variable takes only a discrete set of values, right? So that means the discrete time signals, they cannot take the values on a continuum or a continuous scale of independent variable. That's time in this case. Okay. So the independent variable takes only on only a discrete set of values. For example, speed signal as a function of time and atmospheric pressure as a function of altitude are examples of continuous time signals. Now, for a discrete time signal, if you consider the stock values, okay, for one complete year starting from January 5th, 1929 to January 4th, 1930, which is being depicted in this graph, and this is a weekly representation of the stock, and for each week you have the stock value, right? So this is an example of a discrete time signal. This is a weekly Dow Jones Stock Market Index from 5th January 1929 to 4th January 1930. So there are 52 samples, 52 different discrete values. So it's not a continuum. Okay, for example, this is the first week, this is the second week, then the third week. Okay, and then this trend continues down the line, and then you have about 52 weeks. So these are discrete values over which you're going to have the signal values, okay, so for which you are going to have information over 1 week. It's not like 2.5 or 3.75 or 27.85. It's taking discrete values, okay. So the weekly stock market index, illustrated in figure 3, is an example of a discrete time signal, okay. So to distinguish further between continuous time and discrete time signals, for this course text, we are going to use the symbol T to denote the continuous time dependent variable and small n to denote the discrete time independent variable. In addition, for continuous time signals, we'll enclose the independent variable in parentheses, and whereas for the discrete time signal, we'll use brackets to enclose square brackets to enclose the independent variable. So, for example, you see over here, this is x of 0. This is a discrete time signal. Okay, this is a graphical representation of signals, two signals. This is a discrete time signal in part B, and in part A, you can see this is a continuous time signal. It's taking a value over continuum of time. This is taking a value over discrete time indices, okay, and you can see the notation. This is square. It is the discrete time index is n, and it's enclosed in square brackets. This is parentheses, okay. So again, there's a difference. So you can, for example, in continuous time to discrete time, you can convert continuous time to discrete time. For example, if I have a let's say a switch, okay, now I passed this signal through a certain switch that has a sampling interval, or let's say switching time of Ts, and then you can understand that this switching is only going to happen at those switching instants Ts. So this switching is going to be in fact an integral multiple of Ts. So what you're going to have at the output, if I have a signal, this signal is xt, after it goes to the switch, my signal turns into a discrete time signal where T has been discretized, and instead of T, I'll have NTS, right? That means the information is going to be available. N is an integer, okay? So N belongs to positive integers, okay? It is positive integers. So it will be, so N consists of, so N is, for example, N is 0, 1, 2, 3, and so on and so forth. N is not 1.5, it's not a fraction, right? It cannot be a fraction, right? I mean, the number of times the switch is going to close is not a fraction. It has to be an integer. So the output, for example, will be the sample that I'm going to have is x0 at n equal to 0. That's the initial sample. Then you're going to have, for example, 1, and you have to going to have another sample. Okay, not 1, it's Ts. Then 2Ts, 3Ts, and so on and so forth. And this these number of samples they continue. Okay. So the idea over here is that you see these. If you normalize Ts, okay, let's have Ts. Let's make this more simple. If we have Ts as 1 second, okay, the switching is happening in 1 second, then you're going to have the samples of signal at x0, x1, and x0 and x1 correspond to the samples in the continuous time signal at those particular time instants. These time instants are the switching time instants, right, at which the switch is closing. So, for example, I'm going to have a sample. This x0 is whatever the value, whatever the amplitude of the signal is at t equal to 0, is this x0, right? And similarly, if for 1, whatever is the value, the amplitude of the signal at 1, t equal to 1, so it's this value, x1. So this is x1, right? This is the amplitude, x1. And similarly, for example, this was x0. Then you can go on and have further samples, x2, okay, evenly spaced samples. The switching instant is 1 second. So this trend continues, right? That's how practically how sampling is done in A to D converters. So from analog to digital, you have to discretize the time. So this is a discrete time signal. Okay, it's not a digital signal, but it's a discrete time signal. In a digital signal, you have to discretize the amplitudes as well, right? For example, in a 2-bit A to D converter will have 4 possible values of the amplitudes. Okay, so you have to discretize. So this discretization will be in the amplitude as well for a digital signal. So there's a difference in digital and a discrete time signal. Okay, discrete time signal, is also referred in text as a sequence, because this is a sequence, right? These are numbers, okay? This is not a continuum. These are numbers, right? So for example, these are numbers over here, okay? And for as you will see in most practical cases, this is, for example, this is a non-causal signal. It has indices, it has the negative indices as well, so it has the values for the negative times as well. In most practical cases, for example, if this is a certain system and you're going to apply an input at let's say t equal to 0, you cannot have an output before t equal to 0. Okay. That means the system is anticipating the future, right? So those systems are non-causal or anticipatory systems. We don't have them in practice. So you're going to have the samples only starting at the instant when the switching starts. For example, in this case, the switching started at t equal to 0 and then t equal to 1, 2. Okay, so those are the integral multiple of the sampling instants. Okay, you cannot go in the future and anticipate. Okay, before the switch closes, you have the samples. So these samples, these negative samples, are existing before this positive sample, before this switching started. So this is a non-causal signal. Okay, but anyway, as far as the representation of signal is concerned, non-causality or causality anticipation of future is nothing to do with the representation of the signal. This is indeed a discrete time signal, and you see over here t has been discretized to discrete time index n, which is referring to a discrete time signal. Okay, so graphical illustrations of continuous time signal and a discrete time signal are shown in figure 4. This is figure 4. This is graphical representation of continuous time. A is continuous time, B is discrete time. Okay, so it is important to note that the discrete time signal x of n is defined only for the integral values of the independent variables. Okay, we don't have anything like 1.5 or 2.5 or 5.7, nothing like that. It's not a continuum. Okay, it's discrete, and this discrete does not consist of any fractions. X of n only belongs to the integers. Okay, this n is only integral values. It can take 0, it can take plus 1, minus 1, plus 2, minus 2, okay, so on and so forth. So n, remember that the sequence, the arguments that the sequence is going to take are integers. N is always going to be an integer. Okay, it won't be 1.5 or 1.75, nothing like that. So a discrete time signal x of n may represent a phenomena for which the independent variable is inherently discrete. Okay, signals such as demographic